Hi, I'm Aman, a final year mechanical engineering and industrial design student at Monash University.
Hi, my name's Ben, and I'm also a mechanical engineering and industrial design student. For our final year project, we've been developing a low-cost and easy-to-manufacture mechanical ventilator in response to the COVID-19 pandemic.
This project was inspired by the global situation in March 2020. The COVID-19 pandemic had reached tipping point, transitioning from an epidemic in Wuhan to a global pandemic. The initial outbreak in Italy saw a desperate need for mechanical ventilators, forcing them to make hard decisions about who would get access to their limited machines.
There was a need for additional medical supplies worldwide, which resulted in a new manufacturing phenomenon arising. People in communities around the world who had access to 3D printers were volunteering their time to manufacture supplies for their local hospitals. An Australian effort managed to manufacture 15,000 face shields in just 3 weeks through this method.
The idea of manufacturing cheap and simple ventilators using bag valve masks was not our own. In fact, many teams from around the world have developed designs for these BVM squeezers, providing a rich array of open source collaboration. We saw these BVM squeezer designs as an excellent opportunity to build on the existing work of these concepts, combining them with our own insights and ideas to produce a better LCNV design.
Through our research, we boiled this project down to 2 aims. The first is to design a mechanical ventilator that can be easily used by medical professionals in a hospital environment. And the second is to design a ventilator that can be fabricated through crowdsourced manufacturing methods. We believe that achieving these aims will lead to a unique and functional ventilator design, meeting manufacturability and usability requirements not yet fulfilled by other open source LCMVs.
Introducing AddiVent, a low-cost and easy-to-manufacture mechanical ventilator. AddiVent is primarily made through additive manufacturing methods, which can easily be crowdsourced to members of the community. With this design, a team can coordinate various 3D printing and laser cutting resources from universities, makerspaces and hobbyists to manufacture ventilators within their local community.
It requires no complex hardware or high tolerance manufacturing methods, needing only some bolts, skateboard bearings and cord for its operation. The mechanism is designed to be operational within the constraints of 3D printing. Our unique arm and pull cord design eliminates any high wear mechanical interfaces and eliminates the need for high tolerances in its manufacture.
All moving parts and electrical components are completely enclosed while still maintaining easy access to the BVM inside. It provides a large screen, simple interface within the space-efficient and portable package, making it usable to medical professionals in the clinical environment.
Low-cost mechanical ventilators achieve gas waveform manipulation by compressing the BVM. This solution is advantageous as BVMs are readily available in the hospital setting and can be easily swapped out with each patient. The need for mechanical ventilators was felt in many places around the world due to COVID-19. Italy was the first country to become overwhelmed with the virus, going from 300 to 10,000 cases in just 2 weeks. Doctors in Italy did not have enough ventilators to meet demand and had to make extraordinary decisions on how to triage the limited resources. This is where AddiVent can help by providing a workable stopgap solution that can be manufactured in response to the demand.
During our research phase, we found and reviewed many designs for BVM squeezer ventilators, but these 3 examples embody our major findings. We want a design that has the control system and maturity of the eVent, the ease of manufacture of the Apollo BVM, and the resolved package ready for hospital use like the SpiroWave.
From our benchmarking, we defined our 2 aims, which we mentioned earlier. These aims are really dependent on the design of the BVM squeezer mechanism and the package that holds everything together. These are the areas in which we can really add value. Sophisticated and open source control systems have already been developed by other projects, such as AddiVent from MIT, with the intention that AddiVent control software could be adapted to interface with our design in the future.
Due to our aim of manufacturing through 3D printing, our design would have different requirements to those we saw during our benchmarking. Basically, we aim to eliminate as many mechanical interfaces and high tolerance requirements as we could within the mechanism. Our final design is a unique arm and pull cord mechanism. The motor rotates a spool, which in turn rotates the arm on its bearings and compresses the BVM. The cable eliminates the impacts of any misalignments and can be easily disengaged when needed, and the arm is designed to maintain a constant load on the motor throughout its arc.
Taking a look at the electrical system, its main functional requirement is to allow user inputs control the mechanism, and monitor the outputs of the BVM. The user interface comprises of 4 potentiometers to record clinician inputs and an LCD screen to display vital information. The mechanism is powered by a 12-volt DC motor, motor driver, and rotary position sensor. The sensing circuit consists of 2 6 kilopascal air pressure sensors. Taking a look at the package design methodology, the process begins with a zone and limit volume of the mechanism. This acts as a no-go zone that the package should aim to wrap around. Concepts are sketched over the zone and limit until a direction is picked. The sketch is modelled in CAD to take a 2D idea into 3D space, where the A surface is iterated upon. Once the final surface is signed off, functional B surfaces can be developed to create an assembly of parts that fit together. Finally, parts are broken up into smaller volumes to become manufacturable. Taking a look at the zone and limit, this was developed by making a nominal 20 mm offset over the BVM and mechanism through its motion. The initial surface model was developed as a way of representing the sketch in 3D space. Here, a greater importance is placed on achieving the desired scale and proportion. After 11 A surface model iterations, the final appearance is locked in. The final A surface model provides aesthetic part breakups of the fascia and removable cover. Note that the inclusion of functional handles incorporated into the resolved surface form, with the final beam wrapping around the earlier developed zone and limit, and the emergency stop predominantly placed at the front of the product. Product design renders give us an idea of how the final A surface will look. A monochromatic appearance was chosen as this bodes well with existing medical product design trends. The 4 rotary dials and screen make up the user interface.
The final step is to make the components manufacturable through our crowdsourcing methods. This involves the application of design for manufacture principles to our components. Here you can see the body of the ventilator split into 8 separate parts. These are printed separately and then adhered together to form the final part. Looking at the CAD assembly as an exploded view, we can see all the components coming together. The final design consisted of 18 purchased components, 40 individually printed components, and 3 laser cut pieces. Here is the exploded electrical assembly in detail. As you can see, there is a lot of components mounted in this space, resulting in a compact package with all the electronics completely housed. And here is a detail exploded of the mechanism. A gear interface is used to transmit rotation from the arm to the rotary encoder, which is used to monitor the arm's position during use. During operation, the load between the motor and arm is transferred through the acrylic panels, which are in turn bonded to the main body. This means stresses are distributed through the entire structure of the ventilator. We aim to use a crowdsourced manufacture approach for this project. This means using FDM 3D printing and laser cutting for as many components as possible for this design. One AddiVent uses about 2.3 kilos of filament, equaling to about $81 in material costs. It takes about 10,000 minutes of printing, which sounds like a lot, and for one person with one printer, it'll take a week to manufacture. But crowdsourced to 100 printers, that time comes down to 14 per day. Assembly starts with bonding together the broken up parts. We chose 5-minute epoxy adhesive due to its high strength and short working times. Once the body is bonded together, the mounts are bolted into place. The bonding process is somewhat time consuming, but requires no specialized tools. And accuracy during the bonding process does not impact ventilator functionality. The next step is to integrate the control system from the MIT AddiVent project into our hardware design. After that, AddiVent will need to undergo a verification and validation process to ensure it is safe to use. Finally, the project needs to be consolidated into a single downloadable package, ready to be deployed in response to critical demands.
This project has definitely had its challenges. We started this project right as Melbourne entered lockdown in March 2020. And 7 months later, as we start to reopen, we are able to deliver AddiVent. 7 months of working from home in isolation has resulted in something we are both proud of. Yes, the design isn't perfect. Many of the details still need to be resolved, and adapting a control system to make this operational is no small task. But we believe we've designed a solid foundation on which a genuinely useful and impactful device can be made. Thank you for watching our video and learning about our project.